Hello. In this video we will talk about smart ways to store large quantities of data. I will focus on collection of integers and then you'll figure out the rest. So from our early childhood we remember the following fundamental concepts in C++. Sequence, linked list and stack. Each has some strengths and some weaknesses. Let's take another look at these objects. Sequence is a block of consecutive memory locations. We only keep track of the address of the first term and everything else is in adjacent boxes. Linked list can have its terms and elements all over the memory. They don't need to stick together, and yet nobody will get lost. The first term knows the address of the second term knows where the third term is, and so on. And now about stack. Actually, stack is not worth our time at this moment. It is too similar to the linked list, so we will just give it a spot here at the bottom of the screen and no love. Now, these are the operations that we are repeatedly performing with our data structures. Access, extend, delete, and search. We will discuss how well our data structures are suited for these actions. Sequence will be the first that we will talk about, then linked list, and then we will ignore the stack. It's too similar to the linked list. It's almost the same. So it will stay at the bottom of the screen, but you should tell anyone who is watching this video to just ignore the stack. And so here comes the sequence. Access is very fast. O of 1 is the best grade that the data structure can get. And O of 1 means constant access time. All other grades are terrible for sequence. O of n is the worst insult you can get if you happen to be a data structure. Extending a sequence takes O of n steps. N is the length of the sequence. So even if you want to add just one more term, because the terms must occupy adjacent slots in the memory, there may not be enough room, so you have to copy everything to another spot, and that means n times copying, and that's complexity O of n. Deleting a term is just as painful, and searching for some number in the sequence takes also O of n steps. Linked list can be extended at a constant time. You can see this little star. That means not every extension is efficient. Only adding the term to the end of the linked list has constant complexity. If you want to add something in the middle, that it takes O of n steps. Nevertheless, we use linked lists quite often. Sequences are so bad at extending that you cannot even extend in any direction. Deleting from linked list takes O of 1, but not always, so I'll skip the details. If you want the details, you can pause this video and then figure out which term of the linked list is easy to delete. I won't tell you the answer. Accessing any term other than the first is very slow, and search is also very slow. These are complexities O of n. And now the stack. It is very similar to the linked list, believe me, and let's ignore the stack. Actually, I need this space at the bottom of the screen, so I erase the stack. I made this video because I want to introduce a new data structure called binary search tree. The trees will have very fast algorithms for inserting new terms and deleting existing terms. They will also offer very fast search methods. These algorithms will have complexity O of log n. And in the real world, O of log n is almost as good as O of 1, almost as good as constant. Because even if n is a huge number, like the number of all people on Earth, log n is something like 33. When it comes to binary search trees, we can also make good algorithms for accessing the terms, and the complexity can be O of log n, but we are not going to talk about those in this video. The course website has more detailed explanations and examples of such algorithms. They have code there. So now we are going to talk about the main ingredient of a tree. The main ingredient is the node, and it has three components: content and 2 pointers: address of the left child and address of the right child. And this is one example of a tree. So the first node is called the root, and in this case the root has number 8. 2 children of the root have contents 2 and 9. And so root is 8, and this thing on the left is called the left subtree. And the property of binary search tree is that everything in the left subtree has content smaller than the root, and everything in the right subtree has content that is bigger than the root. And if this rule is followed, then searching is easy and inserting is easy. So let's just look at how we would insert the number 4. 4 is smaller than 8, so it's sent to the left. So 4 is bigger than 2, and now it's sent to the right. 4 is smaller than 7, so it's sent to the left. And we now build a new node. We allocate new memory, and we properly connect that to be the left child of 7, and 4 is now inserted in the tree. So let's just review the terminology. 8 is called the root, arrows are called branches, 2 and 9 are children of 8, and so somehow this really reminded people of trees. So actually, if you ever rotated the tree so that the root is up and the branches are down, then you would get a really good approximation of what computer scientists are thinking when they talk about trees. So now let's again look at an example of a tree and how we are building the tree. So we will work over this very same example again. We will start with the root that has number 8, and we want to insert the numbers 2, 9, 7, 4, 3, and 1 in this order. So 2 goes to the left of 8, and 9 goes to the right. 7 is first sent to the left of 8, but then to the right of 2, because it's bigger than 2 and positioned correctly in the tree. We already talked about what happens to 4. This was exactly the same example, so 4 ends as the left child of 7, and 3 follows a similar path as 4 and ends exactly as the left child of 4. And 1 is the last to be inserted and is the left child of 2. We learned the definition of the tree, and we learned how to insert numbers. Searching procedure is very similar to insert, and let's describe the search on one example. In this example, we want to find out whether 4 is in the tree. So we go to the root and ask, is 4 in the tree? And the root answers, well, I am 8, I'm obviously not 4. However, 4 is smaller than me because you know I am 8. So go to my left child and see if you can get the answer there. So 4 is then sent to the left child. And we repeat the same script. We ask, is 4 in the tree? And the number 2 now behaves like its own root, because 2 is a root of another tree. And 2 answers, I don't know. 4 is something bigger than me, I'm just 2. So go ask my right child. And it's being sent to the right child. Now, we go, the right child is 7, and it wants all the respect. It's its own root, so it wants to be asked the question. So now we ask the question, is 4 in the tree? And we get the response, 4 is smaller than me, so go ask my left child. And finally we go and ask to this tree, is 4 in the tree? And we got the answer, oh, what a coincidence, I happen to be 4. Yes, 4 is in the tree. So the insert and search are very similar procedures. They are implemented recursively. Delete is a little bit more complicated, and we will leave it out of this first introductory video. So we learned how to insert an element, and we learned how to search for an element. And now it's time for bad news. The search and insert may take much longer than the promised O of log n. So searching for number 9 will be fast. It will take 2 operations. We go to the root, we are sent to the right, and in the second operation we find out, yeah, 9 is there. Searching for number 1 is going to take 3 operations, but searching for number 3 will take 5 steps. It will take us 5 steps to conclude that 3 is in the tree. So the maximal number of steps that search can take is equal to the height of the tree. And the height of our tree is 5. And we could be even more unlucky. The order in which we received the numbers can be so bad that the tree can turn out into a single linked list. So then the search would have complexity O of n. Tree would be no improvement over the linked list. And we need an algorithm that creates the trees of small heights. A tree of small height can still have a lot of elements. And those trees of small heights are actually, they look like this, and they're called balanced binary search trees. So balanced trees have small heights but huge capacities. The number of elements grows exponentially with the height. So small heights can have huge number of elements. At height 1 there are not that many elements, only the root. But at height 2 we have 2 children of the root. At height 3 we have 4 grandchildren, and at height 4 we have 8 elements, great grandchildren of the root. And these 8 elements at the height 4, I want to stress how impressive this is. It's more elements than in the levels 1, 2 and 3 combined. Please do count and convince yourself that level 4 has more stuff in than all the 3 above levels. So at the level 33, there are 8 billion elements. So all humans can be put at height 33. Now we will learn about AVL tree and AVL algorithm. This will guarantee that the trees will have small heights. Trees with small heights are fast to search. They also let us insert a new element quickly. AVL trees are named after Georgy Adelson-Velsky and Evgeny Landis. In 1962, these two mathematicians were the first one who discovered that it is possible to create a balanced tree and to keep the tree balanced. Whenever a new element is added, their brilliant algorithm takes at most O of log n steps to rebalance the tree, and the tree always stays balanced. We will now give the formal definition of the AVL tree. The tree is AVL tree if every node is balanced, and the node is balanced if its left subtree and right subtree have heights that differ by at most 1. In other words, the left subtree and the right subtree have the same height, or maybe not the same height, but if the heights are not the same, one of them is by 1 taller than the other. And so the tree that you are seeing at the moment is the AVL tree. Every node is balanced, and now I'm not going to check every node here in front of you. I will check few nodes. So the root has left subtree of height 5 and the right subtree of height 5. Let's check another node. I have highlighted this node that you can now see on your screen, and its left subtree has height 4 and the right subtree has the height 3. 4 and 3 differ by exactly 1, and we are going to look at one more node. This node is also balanced. The left subtree has height 3 and the right subtree has the height 2. An AVL tree can maintain its balance, and that's the whole point of the algorithm. Regular tree loses the balance fast when you add or delete. AVL tree is not a regular tree. When you add something, the balance may get ruined for an instant, but as soon as that happens, the AVL algorithm restores the balance, and it does it fast. The complexity is O of log n. We now describe the algorithm. First, we must assume that we are starting with the perfect AVL tree, and then we add a new element. I will just denote this new element with a blue circle. And there are two steps. Step 1 is insert, step 2 is rebalance. The second step may not always be necessary. Only if the balance is ruined during the insert, then we need to do this clever second step that I will describe now. But let's now first assume that this blue number is actually a number from hell and that it is going to ruin the balance. So we assume first that it's smaller than the root, so it goes to the left. And then smaller than the child of the root and goes to the left again. And then smaller than the child, the grandchild, and it gets sent to this exact spot. So, and this is when we panic. One node has lost the balance. Now go ahead and hit pause. So you should pause this video and try to find the offending node. I have decided that an exclamation mark is the most appropriate symbol to put next to the element that's lost the balance. The left subtree has the height 5. The right subtree has the height 3. These two heights differ by 2. So when a node finds itself out of balance, its two subtrees always differ by 2. And we need to identify the reason behind our misfortune. We start by giving the names to the nasty guys. The node that is out of balance will be called R. Its misbehaving child will be called C. And R stands for root, because R is the root of the tree that is no longer AVL. And as such it will receive all the attention and hate. So the node C has its left subtree that we will call X. Its right subtree will be called Y, and the right subtree of Z will be labeled with Z. Now we can properly articulate our frustration. Bad stuff happens in this blue circle. The node R is out of balance. Its left child C has two subtrees X and Y. X is the evil one. X is longer than Y, higher by Y by 1. Y and Z are of the same height. However, Z starts at a different level. So X is too high for Z because it's by 1 taller and starts at higher level or lower level if you look in this orientation. And this is the cause of our problem. So now we will redraw this picture inside the circle and we will remove all the distractions from it. We will only focus on the devils. So R, C, X, Y, and Z. And this is the picture that tells it all. X, Y, and Z are trees. They may be full of nodes that I decided not to draw. Actually, I had them on the previous slide and then I erased them. So these X, Y, and Z are actual AVL trees themselves. The node R is out of balance and X is just a little bit taller than Y and Z. Y and Z are of the same height, X is taller. X starts at a different level than Z, so it has a head start and is by 1 taller, so that's why R lost its precious balance. And now we need to do something about it. I will show you that manipulating just these 2 pointers can do wonders and restore the balance. So let's start. R's left child will no longer be C, it will be the root of Y, and C's right child will become R. And that's it. So the thing that you are seeing at the moment is an AVL tree. C is promoted to the new root and R has been degraded to the child of C. To see this more nicely, I can update my graphical representation and make this picture prettier. So let's promote C to the root. And so it got this distinguished position at the level of the root. The node R does not deserve to be at the root level anymore, so it is now the child of C. And now I'm going to do the walk of shame for R. It gets pushed down. And as you can see, Z also gets pushed down, but Y stays the same because Y was at the correct level. And now it's time to summarize and see once again our accomplishments. This is what we started from, and after I'm going to zoom this out so I can put more things on my screen. So after the magic, we got this tree. So we started with a tree that was not an AVL tree and got the one that is AVL. It is worth noting that the root has changed from R to C. The parent of R is a node that you do not see in this picture, and that parent has to be updated with this change. So the website has the complete code where we did not miss any details because otherwise the code wouldn't work. So it's time now to realize that we did not cover all the possibilities of how things can go wrong. As you can guess, I covered only the simplest case. And the simplest case is R lost the balance because its left child misbehaved. And how did it misbehave? It had the left subtree X that was taller than Y, and Y was the same height as Z. So, and because X had a head start, it got out of control and disrespected the height of Z. There is one analogous case. Analogous case is this that you can see in the picture. The right node is now C that is misbehaving because its right subtree is the tall one. And this case is actually treated in the same way as the previous one. And you should press the pause button and work out the details. If you press the pause button, I will wait for you. So, the first operation that we described is called right rotation. The name comes from the fact that the original root R was moved to the right. The second operation is the one I did not do in this video. I gave you an option to pause the video and discover operation for yourself. And that operation that you discovered is called left rotation. Right rotation and left rotation are not solving all the troubles that an AVL tree can run into. It's time for a tough one. Now, the left child is again the misbehaving child. However, this time its right subtree is X and is the tall one. You see now the big question mark that I put. I'm going to use it to emphasize that at this moment the solution to this trouble is still a mystery to us. I'll just make it smaller and delay the discussion for a minute to show you one more violent situation. In this situation, the right child of R is misbehaving. We call it C, but the misbehavior happens due to the left subtree of C, which is now too tall. And this one also gets the question mark. The last two cases are analogous, so we will just talk about the first question mark. So it's now time to make this awful tree take the entire screen. The trouble now cannot be solved by just manipulating the pointers that you can see in the picture. I have to play around with some pointers that you cannot see at the moment. I need to break this middle tree X into components and give them full respect and give them the names. So X is broken this way. It has a root that deserves the name. We will call it G. G stands for grandchild. Now the root R has a misbehaving child C and misbehaving grandchild G. G has two subtrees, x1 and x2, and now one of them reaches the same height as y, but the other one goes higher. And our algorithm works in both cases, whether x1 is higher, taller than x2, or x2 taller than x1, it doesn't matter. So that's why I'm drawing them with these dashed lines, because I don't care who is taller. One of them is taller. So we will be able to untangle this mess by using the left rotation and the right rotation that we described previously. So first we will give all our attention to the tree whose root is C. We will now apply the left rotation to the shaded tree. The left rotation is the one I didn't describe. Instead, you pause the video and figured it out for yourself. However, now I need to do the left rotation, so I will actually describe it. So here it goes. Step 1 is right child of C points to x1. Step 2 is left child of G points to C. And step 3 is left child of R. Now the root has to be informed that parent-child relationship is changed, so this is the step 3 where child of R points to G. And now we will just redraw our picture to put the trees at correct levels. G is promoted from the grandchild to the child of R, and C becomes child of G. You can see that we did not get the AVL tree with this one rotation. On the first sight we got kind of mess. However, there is a good news. We are back to the first case that we actually know how to handle. The root R is out of balance, but now the misbehaving child is G, and it has the left subtree that is the tall one. So we perform the right rotation on R. Let's review the right rotation. We did that before. Left child of R becomes x2. The right child of G becomes R. And that's it. We just need to redraw the picture to emphasize that G is promoted. And G goes to a dignified position of the root. This pulled the node C and the subtree Y and X1, so they don't reach crazy heights as before. R is pushed away from this root level to the child. And just one more aesthetic move, I'm going to unshade, to move this G a little bit to the center so you can like this picture a little bit more and unshade this tree. Great news! This video is almost over. Our next task is to implement the binary search tree and to implement AVL tree. I will not let you watch me implementing AVL tree. The course website has all the details and you can download the implementation. I should also be honest with you, I skipped some details. For example, the nodes cannot figure out whether they are losing their balance with only 3 attributes. So it's not sufficient to keep track of only the content and the left child and the right child. We need to keep the track of height of the tree. For every node we need additional attribute height. We also need some additional attributes if we want more advanced features. If you want your tree to allow you to access 30th element, like you want to say, I want 30th element, who is the 30th element, then you need to put more attributes, and each of the rebalancing procedure has to be a little bit more involved. The website also has code for those more advanced trees. So the website also has some good exercises where you can insert things in the tree and then test whether you understood this inserting procedure. And I won't hold you any longer, so it's you should go and practice the things on the website, and those exercises will then turn you into a real tree expert. Okay, thank you for watching. That was all for this part 1 of the video.